So, now after this numerical, let us see about the properties of the DRI which we get it. So, usually the density of the product range is between 1.5 and 4 gram per centimeter cube, or 1500 to 4000 kg per meter cube. Bulk density 1.5 to 1.910 again ton per meter cube. Specific surface area is about 0.5 to 4 meter square per gram. Carbon content usually its range between 0.1 and 0.15 for coal based DRI and up to 2.5 for gas based DRI. So, essentially you can see still it is quite low, the percentage of carbon into it. So, the melting point in that way becomes quite high. So, geometric shape and gangue content of the oxide phase is retained, because there is no slag formation in this DRI. So, whatever gangue is there, it is within that sponge ion or direct reduced ion, so which is retained. High porosity and large surface area lead to reoxidation of sponge ion. So, high porosity is due to the reduction of the oxides, which creates a large surface area, and that lead to the oxidation, reoxidation of it when it is comes in contact with air. So, gangue content is less than 4 to 5%. So, that is why usually then you get about 94% metallization or degree of metallization from most of these processes. And sulfur content, especially in the coal based DRI product, is quite high, because there is no slag which can take it. So, most of the sulfur content is retained into that. So, it is usually quite high. No tramp element like copper, zinc, tin, lead, arsenic, etc. Handling is easier as a solid product. Residual FeO content is advantageous. So, some of the ion which is not reduced or even by reoxidation FeO is formed. This is sometimes advantageous and in the later operation. And the usage of DRI is usually electric arc furnace as a substitute for scrap. Not there. So, that is for the scrap and the electric arc furnace, when scrap is not there, it can be substitute for that for steel making. Similarly, in the basic oxygen furnaces, it is used as a coolant during the blow or substitute for scrap. Induction furnaces as a feedstock, it is used. Open arc furnace now which are not anyway into the market much, it is used as a charge for melting. Ladle furnace is trimming addition, cupola is substitute for cold pig iron. So, there are you can see many uses of this direct reduced iron, and that is where it is used, and you can use them to make the steel directly through this operation. So, you do not need liquid iron in this one, but economically if you consider it is not that much useful when one look at the economy wise, the viability is not that big. So, commercialization of direct reduced processes began in late 1960. So, several of these direct reduction processes have been commercially available now, and have been optimized to a reasonable degree. So many processes started with that, and this is now quite old technology and reasonably sort of optimized and understood. So not much scope to improvement as such. So, and you can see from the latest figure of this, India is the leading country in the production of DRI. So, DRI is production in thousands tons. So, India started a little late, while some other countries, especially the Mexico and these things, they started quite early, and even Russia and Saudi Arabia. But then they didn't go that high. The production more or less in last 2-3 decades is constant. But for India, and you can see from 1990 or so, Iran also, the production is increasing quite high of the DRI. To 2009 or so it peaked, and this one also even in 2015 it has reduced a bit, but not that much, and this sharp drop is because the data were not available that time. So, it is somewhere here those data. So, it is quite high, and India is leading into this, followed by Iran. So, and if you but anyway, if you look at the production, it is there, but it is not very high. If you see, the commercialization of the process started in late 1960, and as I mentioned in the previous slide, that because you get in the solid form the iron and what you need in the liquid form, because finally it has to be melted again. So, economically is not that much viable. When it started, people thought it will overtake blast furnace. So, the recent data show the contribution of this DRI from 1990 to 1916 or so, it just increased by 3%. So, that shows the sort of the progress of this DRI, and certainly it cannot compete the blast furnace or the iron making process. And the DRI which is produced, this shows the major processes. So, one is the midrex. We will be talking about the major process, and SLRN mostly rotary kiln based sort of one, HYL, and then there are few other process, many other which comes there, but not that much commercialized. So, total production of DRI is 74 million ton in 2012. So, this is really constitute about the 4 to 5% of iron production. So, it is not very high due to those limitation of it. Now, if we come to the now we will come to the actual processes after you understood about the kinetics, how does it work and what are the uses of it. Now, the classification of direct reduction processes. We talked a lot about the gas, natural gas as a reducing agent, and then coal as a reducing agent. So, obviously, there are two classification of direct reduced process. One is the coal based and another is gas based. And in coal based process is like rotary kiln, SLRN. There are many processes which are based on this. Then soft drive processes, chem, midrex, electrothermal, So rotary kiln type of this, subtype of this in coal based, where coal is used as a reducing agent, and in the gas based you have a retort processes as well, Hogness, and then some of them fluidized bed, one FIOR, HIV, then shaft furnace bed fluid you have in gas bed. These are again a different this is a Nippon Steel one, HYL3, Midrex, plasma rate and other processes. There are many other processes, but these are some important one, but really as we have seen in the previous slide, Midrex and this are the main, and these two and these are the main processes which are commercially used, and most of the more than 90% production of HR DRI comes through only these three processes. So, we would be talking a little bit only about these 2-3 processes which are similar to others, but only a little bit variation in the other one. So, when we say coal based DRI, so overall reaction in that one we have talked about this is that, and a gas reduction reaction and coal gasification reaction is first order sort of reaction, and this is the one which occurs and by which you produce the iron. And so, rotary kiln, which we said even SLR, and it is on the same principle. So, Spence iron production in rotary kiln. So, what essentially in this it is done that iron ore, coal and limestone. So, like a sort of a composite, they are mixed together and feed a sort of a composite pellets form, and they are put through the tube to the rotary kiln, and there are gas which is supplied through that, and sometimes with the burners through which the fuel is supplied, and mostly from this exit side. So, this is the inlet side of the ore, this is the exit side. The air and coal is a supplied, combustion occurs, and this heat get transferred to the pellets, and it's slowly it increases slowly the temperature, and the reduction mostly occurs in this region, and the hot gases, they sort of heat the material here, so sort of a pre-reduction type of thing, and these hot gases then goes away from the other side where the inlet of the ore is, and after this cooling and combustion of those gases, it goes to the electrostatic precipitator to remove the dust and other and the waste gases, and then the hot DRI comes into the rotary cooler where it is cooled, and then it is gets separated using the magnetic separation. Essentially the sponge iron can be separated. So, sponge iron comes and waste goes another way. So, this is essentially the process for the rotary kiln based and the coal based processes by which directly reduced iron is produced. So, it operates on counter current principle, because the solid is coming from this direction, gas are passing from that. So, it is a counter current principle, gases and solids flows in opposite direction. Gas temperature is maximum 150 degrees Celsius higher than the solid temperature due to the formation of CO. So, maximum the temperature difference between solid and gas is about 150 degree Celsius. Usually it works around 950 or 1000 degree or so. Flux is added to control the sulfur content in the product, which is combined over here in this one, and the temperature inside the kiln for reduction is between 950 to 1100 degrees Celsius. So, it is a solid state reaction, which we have already discussed about those. So, these are sort of the condition in that rotary kiln, and non-coking coal, dolomite or limestone, and final product exhibits a honeycomb structure, with that is why you usually call it as sponge iron or DRI. Magnetic separation is used to separate it with the waste, and 70% of the power generated becomes surplus after meeting the power requirement. So, here the gases which are coming, it is combusted and used for the power supply, and that it is mentioned 70% of the power generated becomes surplus after meeting the power requirement of the plant. Coal based rotary kiln is more popular in those countries where there is a shortage of natural gas resources. So, when natural gas resources are not there, coal based one is there, and also it is quite popular where one does not have a high ranking coal. So, coal based rotary kiln are popular in those countries. The problem which is associated with this very often is a ring formation. That ring formation is due to the low melting compound of this iron silicate aluminate SiO2 as big oxygen, or calcium magnesium iron oxide SiO2 system, that forms a low melting compound, and which deposited near on the wall of this, and that forms a ring, and that is why sticking occurs. So, ring formation, which says the ring formation, and that is a major problem in this. Segregation of charged material due to size, density difference, slope, and rotation of the kiln. So, as you send the material, the name actually said rotary kiln, which means it is rotate, and it has a little inclination. So, by natural weight of that, it comes out the charge from here. So, when it is rotating, usually the centrifugal force and other also works, and rotation of course is very small, due to which actually the segregation of the particles of different size occurs, because by this there is not a close control on the particle size distribution. So, you have some range of the particle size. So, that is why the segregation occurs. So, smaller and bigger particle, and then your reaction also get affected due to that. Process control parameters usually the feed rate, kiln temperature, control of gaseous atmosphere, kiln speed, inclination, retention time of the charge, waste gate temperature and composition. These are sort of the control parameter which are associated with the rotary kiln based processes. Now, gas based DRI processes, as mentioned, mostly it is through the natural gas you do it. So, mechanism of iron oxide reduction is gas based DRI. So, dense oxides reduce into metallic iron by hydrogen and CO. So, that is a mixture of that. You use it in the gas based one with the natural gas. So, reduction rate usually then is faster with the hydrogen than CO. Hydrogen has more reducing power, as we have seen before. Even FeOH and CO system we discussed during the blast furnace one, and we discussed FeCO system also. So, in that one we have shown that hydrogen has much more reducing power than CO. So, overall reaction rate in gas will depend specific rate of chemical reaction, active surface area of the oxide, and the diffusion coefficient of the gas, which is for hydrogen is faster than the carbon monoxide. So, natural gas contains heavier paraffins such as methane, ethane, propane, and impurities like carbon dioxide, nitrogen, sulfur compound along with hydrocarbon. So, usage of natural gas reductant result in the following problem: very slow reduction compared to hydrogen and CO. So, in this form the reducing power of the natural gas is very low, and that is why it is very slow reduction. Carbon soot formation occurs because heavy paraffins are there, leading to choking and unfavorable thermal balance in the reactor. Therefore, conversion of the natural gas to hydrogen and CO is necessary, and that is why where we need the reformer. And one of the slides we discuss a little bit about the reforming of the natural gas, where we saw three more reaction. And so, reforming is the heating of natural gas after desulfurization above 1000 degree Celsius in the presence of suitable catalyst, usually it is nickel or other noble metal, to get a mixture of hydrogen and CO, like this sort of reaction where you get mixture of CO and hydrogen, and this ratio can be controlled using the temperature, pressure and catalyst. So, that is one the essential thing where you need this CO and hydrogen as a reductant or reducing agent. So, increases this increases the calorific value and proportion of reducing gases in relation to the oxidizing gases like CO2. So, reforming is an integral part of the natural gas based processes. So, most popular among sponge iron production processes, this gas based one, lump ore and pellets are charged from the top and reducing gases enters from the bottom of the furnace, similar to the blast furnace, referred as continuous counter current moving bed processes. In this category, matrix process is dominating one and followed by HYL3 and HYL4. So, we will talk a little bit about matrix and HYEL under the gas base, and gas base are very similar to the blast furnace sort of process. So, the Midrex process, this is developed by Midland Ross Corporation of Cleveland, I think it is a Cleveland, USA in 1967. So, as we said, these processes started in late 1960, which we mentioned previously. So, it is a world leader in direct reduction processes. Nickel is used as a catalyst in the reforming system. Pellets are preferred feedstock due to its superior physiochemical characteristics, and even the property can be controlled when you make the pellet instead of lump ore. So, essentially in this one, the natural gas is sent and gets a little bit heated up into this and goes to the reformer, and reformer where we said with the it reform the gas and it gives more CO and hydrogen. So, it is heated up, and with the use of catalyst the reformed gas comes out of it from the reformer, and it is fed into the main shaft or main furnace of that. So, this is the main furnace shaft. From the top, iron oxide or iron pellets are fed, and from the bottom this highly reducible, somewhere in the middle it is send this reformed gas. So, most of the reduction occur over here, and some in this one, even from the side also you send it with some natural gas, and this gives also a sort of a cooling effect. So you can see this a cooling gas compressor, and this gas so this highly reducible gas reduce the iron oxide, and the reduced iron in solid form. So, DRI comes out from the bottom, and these less reduced gases are collected at the top using a gases scrubber to remove dust and other things. And part of it, because still it has a sensible air, it is used for burning the reformer to heat up the reformer. So, it is burned, used as a fuel to burn this thing, and this flue gases also used to reheat those natural gas which is coming out. So, and then these gases goes out to the chimney as a flue gas, and some of the top gas is again recirculated and reformed into this. So, this is also a heat recovery unit, combustion unit and reforming unit, and this is the main shaft where the DRI is produced. So, this is essentially the basic principle of mid-range process on which it is works. As you can see, it is nothing just like the upper part of the blast furnace, and that does not reach to the fusion temperature. So, just above the cohesive zone, whatever it is occurring, that the same phenomena are occurring over here. But here, because CO and nitrogen is there in terms of reducing gas, and so more reducing power it is there, and that's you get the DRI in that way. So, most of the shaft processes are operated in this, but mid-range is the one which is quite popular. It can be adjusted in many ways, quite flexible. So, top case temperature is between 400 and 450 degrees Celsius, is cooled and cleaned in a gas scrubber, and 60% is used in reformer, and rest used as fuel. As I said, some goes again back with that, and some goes as a fuel. So, iron oxide burden is reduced by counter current reducing gas injected at 800 to 870 degrees Celsius through the tuyers. So, this is actually tuyers here. Reduced material undergoes a transition zone before reaching the lower conical section at the furnace, where it is cooled down. Low carbon DRI, less than 1.5% carbon, is cooled in the conical section by cooled gas before discharging. So, it has a very low carbon. So, melting point in that way is quite high. So, never reaches to that high melting point. High carbon DRI up to 4% is produced by passing natural gas along with cooling gas in the cooling gas section. So, you see the here natural gas along with the cooling, you can get a high percentage of carbon, which is probably that Woodard reaction which we saw. So, carbon deposition reaction may occur and can increase it. Decomposition of natural gas occurs due to highly reactive metallic DRI and generate nascent carbon, then absorbed by the product. So, this is also another way can increase the percentage of carbon into the DRI. So, final product is metallized up to 93 to 94%. So, very high degree of metallization.